a lot to cover today. Online, thankfully I've been told, I have the solutions to 2 of the homework questions from section 5.1 that would cause you trouble. You know, the ones with the generalized sigma and so on, what are called Riemann sums. And so you can go there when if you need some help on those questions, and basically gone through it. So what I want to do today is show you 2 more, the last 2 techniques, numerical techniques, for figuring out the area under a curve. These last 2 techniques are pure number crunching. And it's just a matter of, here's the formula, do what it says, and you will be able to get a good estimate for the area under a curve. So I'm going to use this one example to just take you through the process. So imagine that, here we go, got some people coming in. Imagine you were trying to find the area under this curve here, and it was from 3 to 15, and it's got 6 strips on it. So that would be your question, right? So you want to find the area under the curve, and what your first step is, you create this table. In many of the questions, you actually start with a table, so that's one less step to do. So here we've got our 6 strips. What techniques do we know right now to do? Well, couldn't I take each strip and use the left end points? And that would get me L6. I could use the right end points, and that would get me R6. Couldn't I use the guy in the middle and get midpoint 6? So you might think, that's it. How many other ways are there to find the area of each strip? We've done the left, we've done the right, and we've used the middle to get the height of the rectangle. Well, what we do next is we don't do rectangles. Each one of these strips gets changed a little bit. Let's take this one here. See that one here? Can you imagine that it looks right now something like that? That's this point here, that's this point here. Can you imagine joining the top to the bottom like that? And what you make is a funny little shape that is essentially a rectangle with a triangle stuck on top of it. That shape is called a trapezium. So can you imagine this shape was cut into 6, not rectangular strips, but 6 trapezium strips? Can you imagine that? Would you agree that's probably a better fit than a rectangle would ever be? And it is. And it's a better, meaning a more accurate answer for the same number of strips. Now, I guess we're not going to do it this way, but couldn't we take each one in turn and just add up, you know, find the area of that one, find the area of the next, and so on, and just do it physically, you know, by hand? And what we could, but we won't, because some nice fella decide, oh, and by the way, fella, it does not mean you're a male. It's like guy. When I use the word fella and guy, I mean generic, right? Because quite a lot of the guys are girls, right? So that's, if you're wondering, I'm not trying to be sexist. So here we go. T6, trapezoid, 6 strips, right? So left 6, right 6, midpoint 6. It's quite a nice notation, isn't it? The first letter tells you who you're using. T6 means you're using the trapezium rule, 6 strips. Its formula is delta x over 2. This guy's called x0, x1, x2, 3, 4, 5, and so on. And if you find these 6 strips and you add them all up, the formula is delta x over 2, the value of the function f at x0, twice the value of the function at all these guys, plus only one of the function at the end. This is very often called the 1-2-2 rule. So you use this guy once, double all these guys, and use this guy once. And have you noticed that it's not delta x now, it's delta x over 2. So this is just the formula that you use, right? Now you might say, well, where did it come from? Well, if you go and you do if you look up a textbook somewhere, you'll probably see a page and a half, where they actually work it all out and they come up with it for you. But can we just say, yeah, okay, I'll trust you. This thing here will find me the area of these 6 trapezoids added up. So what's that going to look like in practice? Well, I need to know who delta x is. Right, in this picture here, isn't delta x, right, the width of 1? Can you see in this picture it's 2? But if I couldn't figure it out, wouldn't I just take A and B and divide by the number of strips? And I'd still get 2, right? So I could figure it out if it wasn't obvious. If they give me a table of values, so there's no picture, don't I just look at this number and delta x is 2? Right, so it's not hard to get delta x. So what have we got? We got 2 divided by 2. And I should be able to do this in my head, fingers crossed. The rule is one of these, 2, 2, 2, 2, 2, and one of these. So see what that looks like. One of these is 10. Twice that guy's 28. Twice the next one is 30. Twice the next one's 32. Twice the next one is 38. Twice the next one is 44. And remember, only one of the first and only one of the last. So that's the guy that we're going to be doing. And T6 then, well, that's easy because that's 1. So here goes 5, 9, 17, 19, 27. So we end with 7, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So our estimate for the area under this curve is 207. Now, if I did a left or a right, I could have done, right? I could do an L6 or an R6. Couldn't have even done a midpoint 6. And each one of them would be an estimate. But some estimates are better than others. So while we're here, let's show you from bad to good. Right at the top, the worst kind of estimates are L6 and R6. Sometimes one of them's worse than the other, but there's no generic. You know, a different picture, the right is better and the left is worse. Another picture, it's switched places, right? So they're equally bad, right? If you're going to do it, they're simple, but they're not accurate. We now have 2 more guys. Midpoint 6 and trapezium 6. Trapezium 6 isn't as good as midpoint 6. They are very, very close to each other, right? But in general, the midpoint 6 will be a trapezium 6, in general. There are always exceptions, but in general. Now, there's only one guy left called the Simpson's rule. And Simpson's rule is the winner. For the same number of strips, this thing that you haven't found out how to do yet, called Simpson's rule, gives you the most accurate answer. And for all practical purposes, that's the last one that anybody ever uses, right? In fact, for most practical purposes, if people are going to use numerical techniques, they actually go for S6. They just bite the bullet and say, heck, I'm going to do a lot of work anyway, I could do that. Only because you can program a computer to do it. If you had to do S6 by hand and you had to do it with 40 strips, you would not be a happy soldier, right? Because that would be, anything with 40 strips is horrible. But S6, the theory says that it's best. So I guess the question now is, what can we do to generate this new guy called S6? What possible change could you do to a strip that you haven't already done? So imagine the 3 to 5 guy, right? Haven't we done a left triangle? We've done a right triangle. Haven't we picked a middle? Haven't we joined the corners together? We've done everything. So who's left? You join them with a curve. And the curve, if you want to know the theory, is a quadratic. So starting at this point and finishing at that point, they put a little quadratic curve through it. And it's been discovered, oh, and by the way, quadratic curves can also can be concave as convex, right? The best quadratic that could fit through it. And that's what generates the area of your strip. And that strip, you do it 6 times and you add it up. But when you do that, you're not going to do it by hand again, right? You're going to do it using a formula. And that formula would probably take a couple of pages to prove to you, so you don't need to be too concerned about where it comes from. But here it is. Simpson 6. It's now delta x divided by 3. Okay. Trapezium, delta x divided by 2. All the others are just delta x, right? Okay, can handle that. Now what happens? You use this guy once, 4 times the next guy. 2 times the next guy. 4 times the next guy. 2 times the next guy. 4 times the next guy. And you finish with 1 times the last guy. So this is very often the 1, 4, 2 rule. Do you see it goes 1, 4, 2, 4, 2, 4, 2, finishing with a 1, right? And this is called Simpson's rule. Okay, let's see what that looks like. We know delta x is 2, so it's 2/3. One of these guys, 10. 4 of these guys, 56. 2 of the next guy, only 30. 4 of the next guy, 64. 2 of the next guy, 38. 4 of the next guy, 88. And 1 of the last guy. So it's a little bit messy, but I tend to remind myself by just doing this at the bottom. See these little digits at the bottom? That just helps me figure out who gets doubled, who gets 4, who gets doubled, who gets 4, right? So this line here probably would not be written in your usual homework. Wouldn't you probably just go to here? Right, so it's now going to be 2/3. 6, 10, 18, 26, 31. 5, 13, 16, 22, 25, 31. 2/3 311, see what that looks like. 2 times 311 divided by 3. And the answer I get is 207.3. Of all the different estimates that you can use for the area under this curve, whether it's from a table or a graph, this fella here, this 207.3, will typically be the best, most accurate answer you're going to be able to get for 6 strips. Now, there are a fair amount of magic going on here. And I'm just telling you this is the formula and this works, right? And you're just saying, okay, I'll trust you. 4 of this, 2 of that, put it all together, boom, I got my answer. But it is true, trust me. People much better than me have done the deep stuff to convince that the math and our expectations match, and they do. So Simpson's rule is the perfect technique for calculating areas under curves. you can't really do, a calculator shortcut, right? Sigma thing doesn't work with this. It's just too messy, isn't it? But you could probably write a computer program to do it. If you're into computing program, you could probably do that. So if you had to do a lot of strips, you would certainly go to some computer software, probably. Somebody's already written it and use theirs. Is there any questions about using the trapezoid or the Simpson's rule to find the area under curves? I know I've only done one example, but I hope that the gist is there. Does that make sense? Right. Are we good? Okay. Couple of things, not changing anything I said, just a couple of things to mention to you. Do you know that trapezium 6, right, the guy that we just calculated a few minutes ago, if you find left 6 and right 6 and add them together and divide it by 2, do you know that's the same number, the same answer as trapezium 6? Can you trust me on that one? But if you look at the two formula, can you imagine sticking them together and then dividing everything by 2? Do you see it does work? And so in a way, isn't that just the average of the left and right guy? And the second thing is, Simpson's rule needs an even number of strips. So in other words, you can only do Simpson's rule if the shape's cut into 6 strips or 8 strips or 22 strips. You can't use Simpson's rule if it was 3 strips or 7 strips. And the reason that you can't do it is that this pattern, have you noticed there's a symmetry to it? That symmetry only works when there's 7 numbers, which means 6 strips. So that won't be an issue because nobody's going to give you a question, here, use Simpson's rule with 3 strips, right? Because that wouldn't be a fair question, right? It doesn't make sense. But it's worth mentioning in case you kind of thought maybe you could do it with any number of strips you wanted. If you physically were doing a question that you were doing in physics or something, you wanted to find the area and you were going to use Simpson's rule to do it, you have to remember even strips. Apart from that, nothing else. Are we good? Last chance, any questions? I'm moving on. Well, wasn't that a nice short section? Not a sigma in sight, not an n goes to infinity. Here's a formula, plug the numbers in, you're good to go. So let's look at the third section, although it's going to be called chapter 5 too. And this is eventually going to lead up to how to find the exact areas under curves. Not estimates, but exact areas. So I'm going to introduce you at this point to some notation that we haven't used yet, but it's going to be pretty much the notation that will get used. We've been looking at the classic area under a curve problem. Most of the questions have been phrased like, find the area under the curve. But we use this notation. And when you read it out loud, you will say the following. You will say the integral. So think of that as the area under, right, the curve. From x equals a to x equals b of the function f of x. So if I read that out loud, I'll say the integral from a to b of f of x dx. Dx. I added in some extra words because we tend to miss them out. So you'll say the integral from a to b of f of x dx, and what you're asking is, find the area under that curve. Okay, so isn't that much cleaner, concise way of saying it? And we're talking not estimate, we're talking about the exact area when we write this, right? Not 10 strips and it's kind of this number. We're talking about it is this number, right? The exact value. Now, how do you find the exact areas under curves? Well, let's start with geometry. Well, suppose you have a straight line and you want to get the area under the curve from 1 to 5. Now, in the notation that we are now introducing, you would say the integral from 1 to 5 of 4x plus 2 dx. Now, do you see that tells you everything you need to know to create this picture? You see the function? You see where you're going to start your x? You see where you're going to finish your x. If you're wondering where this dx comes from, do you remember the sigma f of x delta x thing? The sigma became this, the f of x is this, and the delta x became that. So the notation kind of came from the Riemann sum to this notation. Well, if I wanted to find the area of this particular shape, which by the way is a trapezium, wouldn't I just find the area of the bottom and the area of the top? Well, I think I need to know a couple of numbers here. Do you see if this guy's 1, won't its x value be, what, 6? And when this guy's 5, won't the x value be 22? And can you pretend I draw this thing to scale? Right, that I did it right. But I've got the numbers. So I'm going to call this piece here A, and I'm going to call this piece here B. So won't our answer just be the area of A and B added together? And I'm not going to do anything too clever. Isn't that just a 4 by 6 rectangle, right? 4 wide and 6 tall. So would that be 24? And this is a 4 by, 6 away from that, a 4 by 16 triangle, right? This is 4 wide, 16 tall, which is 2 times 16, which would get me another 32. And so in this case, the answer would be 76. So isn't the area under this curve 76 units? And it is not an estimate. Isn't that an exact value? Right? You can visually see that it matches the right answer.
Do you mean 56?
Did you catch my deliberate mistake? Yes, I did. Now, what kind of functions can we do geometry on? Unfortunately, really only 2. Straight lines. Any guess what the second and last one's going to be? I know it's a guess, so you don't really know because you haven't covered it. What do you think it might be?
Like circles, kind of?
I would say so, yeah. When you agree a circle is probably a shape that you can handle with. Can we just imagine that I'm doing this circle? And that's 0, and that's 10. And it doesn't actually matter, so I'm not even going to write it down, what the formula for that function is, because that's not going to be what I'll use. Won't I be using this fella? So I'm going to find the integral from 0 to 10 of whatever that function happens to be called, and it might be called something really ugly, f of x. Well, would you agree this is half a circle? And so its area is half of pi r squared. What's the radius of this particular half circle?
5.
5. Yeah. So it's going to be a half of pi times 5 squared. So 25 pi over 2. And that's the answer. Do not turn that into, 75.123 divided by 2 or anything. We want exact answers, so 25 pi over 2, perfect, leave it alone. So as long as it's a straight line or some half a circle, quarter of a circle, something like that, we should be able to find its area just by using, simple geometry, right? I know how to get triangles, rectangles, and circles and put them together. So you might get a shape, in fact, I know you will get a shape, that looks something like this. Still geometry. Let's suppose the shape starts at 1, goes up to 10, then it curves like that. This guy here is 5, this guy here is 13, and then it goes, make it a little bit longer, then it goes to here, and this is, say, 20. So the guy that we're being asked to find the area is this shape, right? And it'll be called y equals f of x. And the question is the integral, say, from 0 to 20 of f of x. Now, to get the area of this shape, actually, it looks a bit like a church, a cross-section of a church. That sheer coincidence, right? To get the area of this shape, would you agree that it's natural that you break it into certain pieces that you could do and then add the pieces together? And I would suggest, and hopefully you'll agree with me, that the most natural split would be here. And I'll get this bit, that bit, and this bit. And I'm going to call this piece A, I'm going to call this piece B, and we're going to call this piece C. So if I can find those and add them up, won't that be the area under the curve that we're looking for? And you take what you get and you figure out a way to do it. So maybe some working at the side would look something like this. If I wanted to do A, for instance, wouldn't I probably break it even further into 2 smaller pieces? And the bit at the bottom is a 5 by 1 rectangle. And then the triangle at the top is a 5 by 9, right? 5 wide and 9 tall, right? From 1 to 10 is 9. And half of 5 pi, that's 45 over 2, I believe. And let's look at B then. To do B, would you agree it's probably natural to break it that way? Looks a bit like a doorway now. The bit at the bottom is what, 8 units wide by 10 units high. So that would get me 80. What's the radius of this half circle?
4.
Okay, you're right. You want to explain to maybe some of them who are thinking, I wonder where that came from? You are right. How'd you do it?
The distance from 5 to 13 is 8, and then you just divide that by 2.
Make sense? Agreed? Yep. So it is half a circle, so won't it be a half of pi times the radius squared? 16, half of 16 gets you 8, so that's 8 pi. And then the last piece, which I'm calling C, oh, that's an easy one. Isn't that 7 by 10, which is just 70, right? 7 this direction, 10 that direction. So the entire area that I need is made up of this guy, this guy, and finally That guy. And so what I've got, I'll put the 8 pi at the front, right? That's that taken care of. That's 150. I got 80, I got 70, I got 5, and then I got this weird 45 halves thing. Right, if you add them up, don't you get 155 and then 45 halves thing? That's not good math. You don't do that. And I know that there's a temptation to call that 22.5 and add it and do something, but we really want a fraction where everybody's over 2. So that's 310. So are you happy about 355 over 2? That's 310 halves, another 45 halves, 355 halves. We do not like mixed fractions in math. So 7.5 is considered bad form. We prefer 15 halves. So calling this 177.5 isn't as good as 355 halves. So a little nitpicky, but you could find that you did the right answer, but because you wrote it as 4.5, the WebAssign won't give you it, right? It'll say you're wrong. Are we good? So as long as it's straight lines or pieces of circles, we can get exact areas. Pretty limited, but you know, it's something. So where am I off to now? Well, I'm going to show you something that is a total contradiction to what you've probably been told in the past, but it's true. Suppose I want to find the area under the curve. So the area under the curve is basically this shape. And this is the first time we've ever had the thing go below the x-axis. Right, so we're going to have to figure out how that is going to work out, because it is going to be something that sounds like it's wrong, but it's not. I'm sure you've probably been told a particular sentence I'm not going to use right now till later. If I call this top piece A and this bottom piece B, shouldn't the integral from 0 to 12 of this function, right, that's how we would write that, represent this area under the curve? Now it's made up of 2 pieces, an A and a B. Well, let's take care of the A first. Would you agree that's just a simple triangle? Whoops, I need to tell you where there is. 6. Isn't it a 6 by 3 triangle, right? 6 by 3. And half is 6 by 3 is 9. Now this triangle is 6 by 5, right? 6 by 5. And half is 6 by 5 is 15. Here's the sneaky part. This guy is negative. So when we in mathematics in Calc 2 talk about the area under a curve, the area is allowed to be a negative number. In this case, the net effect of these two is -6. And that's a contradiction in your brain, because I'm sure you've been told you can't get negative areas, right? Nobody goes into the shop and says, I want -6 square yards of material, right? It has no physical meaning in that context. But it does have a physical meaning in some of these situations. Sometimes the area that we're about to calculate under the curve represents velocity, right? So if you do an acceleration time graph, where sometimes acceleration is positive, but sometimes acceleration could be below the axis, right? It could be negative. The area under that curve is the net velocity, right? And do you know velocities can be positive, you're going up, but can't velocities be negative? You can come down. Aren't you also allowed to have positive and negative displacement, which is basically position? Do you know the area under a velocity time graph tells you the displacement during that journey? Because those situations do often end up being negative, do you see why negative areas now have a contextual reason to make sense? Right. So I'm not talking about negative 6 square yards of material. That is still stupid, right? That's just a nonsensical result. But can't I talk about negative 6 meaning your total displacement is 6 feet below where you started? Or your velocity is negative 6. You're going downwards towards the earth rather than going vertical upwards. So negatives are allowed. So if I return, if I can find the darn thing, probably won't now. Remember this guy here, the one we already did? Okay. Can you imagine that some of these pieces could be below the axis rather than above? And that could mean that when I add these things up, couldn't I get some adds, but also some negatives? And it isn't unlikely that in some circumstances, if there's more of the shape below the x-axis than there is above, won't that probably end up with a negative final answer? Right, if there's more below than above. It also, this property, allows me to do this very special case. Can you pretend that I'm good at drawing? And that is the sine function between 0 and 2 pi. Can you pretend up and down? Sine function. If I wanted to know the integral from 0 to 2 pi, that's the area under the curve, of the sine function, I know the answer to that question. I'm not going to use geometry because that isn't half a circle, even if it looks like a half circle to you, it's not. If you put a half circle on top of it, it would be different. It would be a little bit squashed. But I do know what the answer is. Agreed? What's the answer?
0.
0. Because by symmetry, don't we know that for the sine function, this bit and that bit are the same size? The fact I don't know what they are doesn't matter, because if they're the same size and one's plus and one's negative, doesn't that guarantee 0? So we are in a very few, very specific situations, aren't we now able to get exact values for the area under curves? We either do geometry, rectangles, half circles, or we occasionally might get lucky where the shape's got some symmetry and we know this bit's the same size as that bit, and so the answer is 0. And we're good, right? So in that same vein, let's suppose that by some miraculous method that nobody knows yet, you're told the answer to a particular question. Let's suppose that you're told that the integral from 0 to 2 of x squared, right? So somebody went and sketched x squared from 0 to 2, and they found out the answer was 8/3, which actually is. I can use that guy to find the answer to that integral. I only know this, but I can use this to tell what that is. If the world was nice, wouldn't it be a very simple way to do it? You can take out the 5 and can you see that your answer then is just 5 times what that guy is? Looking good? Let's suppose I tell you that the integral from 0 to 2 of x cubed was 4. Could we use this given piece of information to get this guy? You see where this is going, don't you? Can I skip out that line and just say it's going to be -3 times 4? It's -12 and it's okay to be negative. We can do better. If you tell me what this is and you tell me what this is, I can also tell you what this is. Can you see where this one's going? Don't you use these guys as your building block for any combination of these guys? So basically, won't you get 5 of this fella, which we've already done, and minus 3 of this fella? And you probably want to make this guy 36 thirds and that guy and that size. So 40 take away 36. I believe the answer is 4 thirds, but you can check it later if you want. So if you can give me building blocks, if you can tell me this is what this particular area under the curve is, can I get any linear combination of that guy, right? 3 times it, 5 times it, a half, minus 4 of it. If I know 2 functions, can I do any linear combination of those 2? 6 of the first one, add 2 of the second, any combination you like. And won't those be the exact values of those particular guys? Looking good? Intuitively, does it kind of feel right? That's how you would have done it if nobody told you how to do it. To me, that's what intuitive means. Yeah, that seems reasonable or sensible. I think this is going good. I'm not 100% sure it is going good. Okay. So let's put in some ugly ones. Suppose you are told that this guy here, give me a second, I have to do it to tell you the right answer. Was that? Who cares? That's what it is, right? That's the answer. It just happens to be that because I'm telling you this. Could we use this to get that? What would I need to do to this answer to get the exact value for this area under the curve?
Pull out a 3.
Yeah. And can we just cut to a chase and say that would be it? Are we comfortable then if I tell you something, you can use it to get multiples? I guess that's really what we've been doing. And if I tell you 2 things, can you put them together like 4fx and 3jy's and things like that? So this is how it might look in a much more generic way. Suppose I tell you this guy's 7 and this guy's 4. Shouldn't we be able to figure out who this fella is? Now, you notice it's the same thing that we've been doing, but now it's generic, right? There's no particular formula here and no particular function formula here, but you know it's 2 of this guy and 3 of that guy. If you were setting it down, wouldn't it be 2 of this guy minus 3 of this guy? And I believe that's 14 add 12, so the answer would be 26. So the property that we've learned doesn't even care if you don't know who f of x and g of x is, because really all you need to know is what the area under the curve of it is, not what the function was called. How about this? This is different. The integral from 0 to 1 of f of x, we'll keep it generic, is equal to 7. And the integral from 1 to 3 of the same function is 10. What would the integral from 0 to 3 be? So this is a new puzzle. The area between 0 and 1 is 7. The area from 1 to 3 is 10. So what would the area starting at 0 and finishing at 3 be? Or at least how would you get it?
Wouldn't you just add them?
Isn't it nice when things come out the way they should? Does it make sense why she said that? Kathy, what was your thought process behind that? Did they just seem obvious, or is there a way to explain it?
Well, they were both areas, so if we need the area in both of those sections, we would just add the areas.
Right. Yeah. I mean, if you're a visual person, I know this isn't accurate, but can you pretend that from 0 to 1 it was this fella, right? And then from 1 to whatever, 3 it was this fella. When you just add them together, and that would be the area of the whole fella. That one went pretty good. Try another one. The integral from 4 to 10 of g of x is 20. The integral from 4 to 6 of g of x is 5. What's the integral from 6 to 10 of g of x? And it's not 25. Look very carefully at what I've told you. You agree it's not 25. Any suggestions how to find that? What is the answer to the integral from 6 to 10?
Take 1 from the other.
Uh-huh. And the answer is 15. Now let's geometrically figure out what the heck's going on. If I tell you from 4 to 10 is 20, aren't I telling you that that whole chunk there, right, the whole kit and caboodle is 20? Now, if I tell you 46 is 5, so I'm just telling you this bit is 5. And now I'm asking you for this bit. Does it make sense that 20 cut off 5 is what the other piece has to be? Right. The whole thing's 20. The first piece is 5. The other piece is what's left, 15. Right. The whole picture is 20. This piece is 5. This little piece in here, what's left? So we can find exact values for areas under curves, provided you give me some building block information, right? Can you at least tell me what something else is, right? Can you tell me the integral of x squared? Can you tell me that bit? Can you tell me what integral of f of x is between two numbers? Those kind of building block pieces of information will then allow us to pretty much find the exact value of all sorts of other pieces. Are we good? Oh, goodness gracious.